We now introduce one further application of derivatives. And this is a bit circular in the sense that we use limits to define derivatives, and now we're going to use derivatives to help us evaluate some kinds of limits. So bear with me on that. This rule is basically given here. If we try to find the limit as x goes to a of some ratio, so that's the key thing here, it's a ratio of functions, and if it gives us the form 0 over 0, then L'Hopital's rule says if you have that form, you can trade out your original limit for this new limit, and the two limits will be the same. So this new, hopefully easier limit should give us the same answer as the original limit would have. And it turns out it's not that hard to show this as being a derivation from Taylor polynomials, because if we take the limit as x goes to a of f of x over g of x, and what we just said here is f of a is equal to 0, and g of a is equal to 0, then what can we do? Well, we can replace f of x with its Taylor approximation, f of a, f prime of a, x minus a, all over g of a, that's what g of x could be approximated by, plus g prime of a times x minus a. Well, what happens next with that? Well, oh wait, these things won't usually, these two will not be usually the same. However, under the special case that the function at a and the bottom function at a both give 0, let's sub that in, we can simplify a bit. We'll have x goes to a of 0 plus, well, the 0 doesn't matter anymore, so it's just f prime of a, x minus a, over g prime of a, x minus a. And wait, we just said, well, those guys can cancel, that's easy. And wait, that's just exactly what we want here. That's the limit as x goes to a of f prime of x over g prime of x. So we have a limit, if we start with a limit that has 0 over 0 as its form, if we swapped out, as we did earlier in this unit, for the, let's say, the linear approximation here, when we cancel things, we would get the ratio of the derivative of the top versus the derivative of the bottom. It's important to note that this is not the quotient rule. Okay. The quotient rule is no limits, differentiate this ratio. When we have a limit question where we're asked what's the limit of this over this, and it turns out to be 0 over 0, then we can replace it with the derivative of the top separately and the derivative of the denominator separately. All right. Here it is a little more formally. It also turns out, though it's harder to prove, that any of these indeterminate forms, 0 over 0, plus or minus infinity over infinity, whenever we have those, then we can take the derivative of the top, take the derivative of the bottom, and then take the limit after that and see what we get. The two limits will be equal to one another. Let's see this in practice. All right. We'll take the limit as x goes to 0 of 1 minus e to the negative 2x over x, and we check. First thing is to check for indeterminacy. Indeterminate. Is it actually a 0 over 0 form? And yes, it is. It's 1 minus e to the 0. Well, that's 1. That's going to 0. That's definitely 0 over 0. If that's the case, then the limit as x goes to 0 of 1 minus e to the negative 2x all over x is going to be equal to, using L'Hopital's rule, it's going to be equal to the limit as x goes to 0 again of the derivative of the bottom. So let's do that here. We take the derivative of the bottom, and that simply gives us 1. So we can see where the problems are going to vanish with this. Instead of dividing by 0, now we're just dividing by 1, which is fine. Then we also have to take the numerator, differentiate it, and we'll get 0 minus e to the minus 2x times minus 2. And that will give us, with some tidying, the 1 doesn't matter anymore, dividing by 1, we'll have 2e to the negative 2x. This is now a simpler limit than the original. And with that limit, we simply get 2e to the 0, which is 2. So in this scenario, we traded a limit that was indeterminate and which we couldn't do nice cancellations with. We exchanged it for a second limit that was actually easy to evaluate by subbing in. And that's usually the application of L'Hopital's rule. Let's do it again, except now let's try it with the infinite limit. Before we start, though, we should check what happens when x gets bigger and bigger here. We have 1 minus e to the large negative number actually is 0 all over infinity. Well, actually, this is just 0. We're done. We're done. It's 0. Why is it 0? Because this is not an indeterminate form. As x gets bigger, this term vanishes. We get 1 over a larger and larger and larger number. The limit's going to be 0. There's a horizontal asymptote of this whole thing. So L'Hopital's rule is not needed here and actually would not work correctly in this scenario because we don't meet the requirements for it. We don't actually have an indeterminate form. So we can just take the limit in the old-fashioned way. Let's try another one. Practice makes perfect. So we have 1 minus cos of 4x over x squared. And let's just check. Again, check for indeterminacy. We have 1 minus cos of 0 if we just try to sub in. And that is, in fact, 1 minus 1 over 0. That's 0 over 0. Okay. We cannot work with that because that is indeterminate. So what do we do? Well, we can use L'Hopital's rule. We're taking the limit as x goes to 0 of 1 minus cos of 4x all over x squared. And through L'Hopital's rule, we'll just call it LOP, we can trade that limit for a new one. We're going to trade this limit for the derivative of the numerator, and that'll be negative. The derivative of cos is negative sine. And we have a 4x, so we'll have a 4 from the chain rule. Then we're going to differentiate the denominator, which will be simply 2x. Now that we should tidy before we do anything else. X goes to 0 of 4 sine of 4x all over 2x. And let's tidy that up some more. So basically 2 sine of 4x over x. And now we try to sub in. So we'll put 0 sine of 0. Oh man. Sine of 0, 0. 0 in the denominator as well. That's still indeterminate. Well, nuts. What do we do now? Well, this is just a new limit. I'd like to know what the limit of 2 sine of 4x over x is. Well, let's try and figure that out. Well, L'Hopital's rule can come to the rescue there too. This is just a new limit. We're going to build something that's equal to it through L'Hopital's rule, which we're allowed because it's indeterminate. The limit as x goes to 0 again of 2, differentiating the top here, 2 cos of 4x times 4 all over 1. This is lovely. That's the limit as x goes to 0 of 8 cos of 4x. There is no problem evaluating this. We sub in the 0 into cos, and we get 8. And what L'Hopital's rule means, or tells us, is that this 8 for this other limit goes back to the first limit. Oh wait, that limit came from our very original limit. The limit as x goes to 0 of 1 minus cos of 4x all over x squared will equal 8 as well. That's what L'Hopital's rule guarantees us. Last but not least, let's try a little variation here where we have the limit as of x times ln of x. In this scenario, what we have is a different kind of indeterminate form. We're going towards 0, so we have 0 times, well, ln of 0 is actually minus infinity. That's another indeterminate form, but it's not a ratio. And if we don't have a ratio, we can't divide or differentiate the top and bottom. So what's our trick here to use L'Hopital's rule? Our trick is going to be to make a ratio out of this. One way or another, we'll make a ratio out of this. Well, how can we do that? Notice we have the 0 from the right. That's just to make sure that the ln is defined. We can't plug in negative x values into ln. But if we're trying to find the limit as x goes to 0 of x ln of x, how could we rewrite this? There's a couple of options. I think the most natural one is to take ln of x over 1 over x. That new limit is now negative infinity over, well, if x is going to 0 from the right, this would be positive infinity. That's definitely indeterminate. And it's now in ratio form. So we can use L'Hopital's rule. So we'll go from here to here. Using L'Hopital's rule, that'll equal the limit as x goes to 0 from the right of the derivative of ln of x, and then taking the derivative of 1 over x, be careful with all this, that's the same as x to the negative 1. We get negative x to the negative 2. Let's rewrite this as 1 over x, that's that, times 1 over minus 1 over x squared. That's x to the negative 2 in a denominator. And we need our limit. We can't leave out our limit. But our 1 over x stays there. This is 1 over x squared. That's better known as x squared. There's a negative sign. We keep that. And then we can say, what's the limit as x goes to 0 from the right of negative x squared over x, or x, simply negative x. And that's going to be what happens when we plug in values of 0 into this. We get a simple 0 value. So it started off looking indeterminate as a product. To be able to use L'Hopital's rule, we had to make a ratio. But once we make the ratio, we can use the same rules we've been doing. The limit will be the same as the limit of the same ratio, but differentiating the top and the denominator separately. There's lots of practice in the practice problems. Please take a look at that. And again, always feel free to ask questions if you have any.